Welcome to Math 105, Chapter 8.2, where we talk about Bernoulli trials and binomial random variables. So Bernoulli trials is an experiment which has only two possible outcomes, right? So with two outcomes, you can only be a success or a failure. So that's what it means by binomial. You can either be a success or you can have a failure. So in our experiment, can you roll your dice 20 times and record your findings below? So all of your other findings right here. So whether you use the app or you're in class and you roll the dice, I'm just going to quickly put one down that I did before. Okay. Now let's define your X. So you've rolled your dice, and now let's give this a experience meaning. So let's say X is really the number of times a 5 was rolled. So in our case, we're looking for 5s. So a 5 is popping up here and here, right? Which means, let's see, which means our frequency. So when we're looking at X is equal to 2, right? This is just meaning that a 5 occurred 2 times, right? We were successful twice. So in our case, what is the probability that X is equal to 2? We successfully rolled the dice twice to get a 5. Well, we had 2 out of the how many rolls? Well, we had 20 rolls. So we had 1 out of 10 or 10%. So then what's the probability of failure? So if this is success, what's failure? Well, because there's only 2 outcomes, if we were looking at 5s to be successful, then the remaining values that we got are going to be considered failures, right? So we can either spend the second and like count all of the remaining that are not successful, right? But the probability of failure is the opposite of success. So the probability of failure is 1 minus your success. All of a sudden I cannot sorry, someone's trying to get my attention. 1 minus 0.10, which equals 90. I'm so sorry. Look at your phone. I'm sorry, guys. Oh my goodness, my apologies. Okay. The probability of failure and the probability of success. Now, how is our experiment different from the ones that we had done yesterday? Well, the ones that we have done yesterday, right? We said this one, we're going to roll until something happened. This one, a little more similar. We have a finite amount of times that we have to roll. This one was 15. Ours is now 20. We're observing that the number facing up is our success, right? Except we did not consider the remaining as failures. Instead, we could also have determined the probability of this, but individually, like we did on a probability distribution. So in our case, ours is slightly different. We have a terminating value that we have to finish after a set number. But the remaining values of your probability are considered failures. So now we're going to define a little bit as to what your probability of success is. So probability of success, so if P is the probability of success, then the probability of failure is Q is equal to, now how did we find the probability of failure from before, right? 1 minus success, or 1 minus P. So think about this being the event in the complement of E, right? Not E. Always we want to negate or subtract out. Now your trials are independent, so what happens previously is not going to change what happens next. So whatever your experiment is, right, we have your success, we have your failure, so this being P, and then 1 minus P to be equal to Q. Okay, so when we do your branches, you have success up here, or I mean, order doesn't really matter, but you have success branch and then failure branch. Now a sequence of Bernoulli trials is one that counts the number of successes in a sequence of independent trials where the number of trials is fixed. So that's what we ended up doing here. We did a sequence of the experiment. Now, if we wanted to do it again, for example, roll a dice 10 times, or, and this time maybe counting rolls 6, so something that we kind of just did. Or perhaps this experiment, we flip a coin 3 times and X is the number of heads that occurs. So what now usually if I go back to that coin toss, or not coin toss, yeah, coin toss. Let's see, what was I just gonna say? Oh yeah, so not the coins, the rolls. So typically on a dice roll, right, if we're counting the number of 6, so P typically is 1 out of 6, right? However, now if we're saying P is success, then in order to roll a 6, right, this one happens to be 1 out of 6, but Q being your failure, instead of the remaining numbers being 1 out of 6, 1 out of 6, 1 out of 6, your failure is the opposite. Your failure is now 5 out of 6. Now, when we're talking about your coin toss, now coin toss is a little different because your probability doesn't change because there's only 2 sides, but I definitely want to show you on your dice roll, right? The opposite now for the remaining numbers is going to be a lot higher than what we've seen before. So on a coin toss, even if P is your success, it's going to be not 1 out of 5, 1/2. In Q, the opposite will also be 1/2. No matter if this is a regular experiment or a, what are these called? Bernoulli Trials. So what I'd like you to do now is to pause the video and see if you can come up with the sample space of all of your coin tosses, a toss being 3 times. So we have heads, tails, heads, heads, tails. Okay. And your sample space. Okay, so these are all of your sample spaces. So let's just define that out. So this is your sample space. Now let's bring some meaning to our experiment. We're going to say X is the number of heads, number of times a heads occurs. Now we've done this experiment before. Now we're going to show it as a Bernoulli trial. So number of heads showing. So in this case, right, we had 3 heads showing. So we have X is equal to 3, or 3 successes. Then X is equal to 2. Another one. X is equal to 2. 2 successes. So take a moment to define the remaining. Got 1 success here, another 2, 1. There we go. Now you can certainly make a probability distribution as we've done before. It'll certainly look just the same, right? But now what we're going to be doing is showing you that we're going to be increasing the amount of coin tosses when it's a little bit harder to determine with sometimes a decision tree. Now, the most that you're going to see in our class, I think, on a homework is probably 4 coin tosses, but one in your textbook had 5 as well, which it's really hard to get a decision tree going for something like that. You can certainly do it. However, this is kind of a shortcut method to show you what you can do instead. Because decision trees are great to lay out what your sample space looks like when it's working with a series of very similar similar experiments being performed. But it's not great when there's a lot of outcomes being produced. So instead, we can do something like this, where we're talking about a sequence of independent trials to have this formula. So this formula goes to say the probability that X is a randomly selected number, where this small x is the number of successes that we've just defined, which is equal to NCR. So we do this piece because there's so many outcomes that a decision tree is no longer a great fit for us. So instead, we can kind of shortcut that method to find all of the different outcomes. When you find all of the different outcomes, then we can multiply the probability of success times the probability of your failure. Failure having the exponent of now your like unsuccessful trials. So let me define this out just a little bit more. So this x here, and any of those x's that you see following, this x is the number of success. Same here, this is the number of success. And same here, the number of success. Now the remaining, let's see, this one here is just the total number of trials. P is the probability of success. Q is the probability of failure. And N one more time is the number of trials. So you can certainly be sure that when you add these two exponents together, that they come back to make the number of trials. So let's try it in example one. Now we're not going to do too many tosses. We'll just keep it basic with the 3. But this is really great when you have more, like when a decision tree isn't a great fit. So example 1 says, use the decision tree and let x be the number of times a head occurs. What is the probability that the number of heads is exactly 2? So what we're looking for is the probability when your success is 2. So in our case, the probability that x is equal to 2, the number of successes, is equal to NCR. So how many trials did we do in your decision tree? How many coin tosses? Well, we did 3 coin tosses, of which we're looking for our success to be 2. Actually, I'll just write everything in black and then I'll highlight. Times the probability of success raised to the second, right, being the number of successes. So we said coin tosses are 1/2 raised to the 2 times the probability of failure, also 1/2 raised to the 3 minus 2, which is 1. So again, I'm just going to define that out for us where things came from. We have 2, 2, 2, and 2 here. We have 3 here, 3 here, and then your 50-50. So let's put that into your calculator. I'll do Desmos first. So we said 3, choose 2. And then we said we're going to multiply that by 0.5 raised to the 2 times 0.5. And I'm going to show the exponent no matter what. I know it's just 1, but we have 37.5% or 3 out of 8. Or 3 out of 8. So then what's the probability of the number of heads is exactly 3? Well, exactly 3. Let's try it again. And I encourage you to pause the video. So 3, choose 2. Nope, 3, choose 3. 0.5. Third times 0.5. 3 minus 3 is 0. And no, that does not make this 0. It actually makes it 1. And this choice, anytime it's to itself, is also 1. So it's really just this probability that we're looking at. But I'm going to just make a small edit. Three, and one more. So we get 1. And again, all of that should look very similar to your decision tree and your probability distribution from last time, because I didn't step up the number of coin tosses. So this one is pretty manageable. Now, what's the probability that the number of heads is 2 or more? So the probability that x is greater than or equal to 2, well, it's really the probability that x is equal to 2 plus the probability that x is equal to 3. Because then when you run out of trials, then you can stop. So our trials only being 3. So we had 3 out of 8 plus 1 out of 8, which equals 1/2 or 4 out of 8. Now I'm going to pause and see if we can do one more, just increasing the amount of tosses. So let's try it again, where n is equal to 5 tosses, and the probability, or sorry, the x, we're looking for the probability that x is equal to, let's just do 4. And we're still talking about coin toss. So toss. So pause video, see if you can do it one more time just by switching your number of tosses. So we have 5, choose 4, the probability of 0.5 to the 4th times the probability of success, 4, sorry, 5 minus 4 is just 1. So we're going to make that a little error. Let's see. 5, choose 4. 4 and 1. So 5 out of 32. And there you have it. Okay. So slightly bigger. You're going to be seeing these a lot on your homework, and hopefully they're going to be quick and easy. All right, one more for example 2, and then that is a wrap on 8.2. So pause the video, see if you can make a distribution table, and then answer the following questions. So it says, by 2030, the probability that a randomly chosen resident in the US will be 65 years or older is projected to be 20% of 0.2. What's the probability that a randomly selected sample of 6 US residents is exactly 4 of them will be 65 or older? So we're being told that we're trying to choose a person that's 65 or older. And the probability of that happening is 20% or 0.2, which means failure is what? 1 minus 0.2 is 0.8. Okay. So we are looking now for exactly 4 residents. So that's going to be our n is 4 to be 65 or older. Oh, so sorry, that's not your n. That is your success. The probability that x is equal to 4 here is your probability of success. In our case, we're talking about sample of 6 US residents. I got that backwards, 6 here. 4 of them are our success. So we're starting off with 6, choose 4. times 0.2 to the fourth times 0.8 squared. That should give us, let's see, I can't read my handwriting. I got to zoom in, 0.01536. Round just to what you believe is the best. I started off with 3 and then I had to go up all the way to 6 decimal places on our distribution table. So let's try it again now with that distribution table. So keep in mind we have 6 total, so we can either have one success, or sorry, no successes. 1, 2, 3, 4, 5, and 6. We already found one of them, 0.01536. Now you don't have to do all 6. I would pause the video and do maybe the first 2 or 3, get the hang of it, and then jump back. All right, so I won't talk for too much. I'll probably just do the first 2, and then from there I'll be silent and kind of just keep working it. So if we're looking at 6, choose 0 times, times 0.2 to the 0 times 0.8 to the 6. Got that. Copy. We're going to paste it here. Maybe I should just copy the empty. Okay, so when you put this into your distribution table, this should come out as 0.262. And then again, for 1, it's 6, choose 1, to 0.2 to the 1, 0.8 to the 5. This should get 0.393. We're going to keep going. Now the number of trials is 2, or sorry, successes is 2. Going to flip-flop 0.246. And now I'm just going to write as we go, because it gets very repetitive as you're seeing. 3 and 3. We already did 4. And last one. And there you have it. So that is your distribution table being completed. Now we can certainly ask a number of questions. Perhaps we want to figure out, okay, what's the probability that the number of randomly selected residents is greater than or equal to 2, right? So in this case, what would you end up doing? Well, we can add all of these probabilities up, right? Now that's a lot to add, or you can subtract the undesired from 1. 0.262 plus 0.393, or you can add the probability that it's 2, probability that it's 3, and you keep going, the probability that it's all the way up to 6. And that's it. All right, hopefully that lecture made sense. Make sure that you're on the lookout for any time you have just 2 variables, so whether you succeed or you fail, instead of a much larger amount. Usually they tell you that. Sometimes it's just kind of context clues in the problem.